My name is Büşra Baykan Mercan. I am a mechanical engineering master degree student in Top University of Economics and Technology in Turkey. Welcome to my presentation about failure prediction of composite open-hole tensile test specimens using bond-based peridynamic theory. First, I'm going to talk about studies done in the literature. Then I will tell you about the objective of study, and I will continue with method used for the solution results, then discuss the conclusion, and finish with future work. Peridynamic is a non-local theory introduced by Sealing in 2000. A non-local theory is that a material point is affected by material points located in a region of a finite radius. Basically, the peridynamics is a reformulation of equation of motion in solid mechanics. The theory uses spatial integral equations, which make it easier to model discontinuities. The original peridynamic theory, invented in 2000, has been later called bond-based peridynamic. Then Oterkuş and Madenci have presented an application of peridynamic theory to predict how damage propagates in fiber-reinforced composite materials under mechanical and thermal loads. Problems have been analyzed in fiber direction and arbitrary directions. Therefore, two peridynamic bond constants have been determined for each direction. Failure mechanisms as matrix crack, fiber breakage, and delamination were examined. They came to the conclusion that peridynamic theory is successful for failure analysis of composite materials. Killick et al. Did a research on peridynamic theory using 2-ply and 3-ply laminate with different lamina orientations with a center crack. The peridynamic results was validated with experimental data. The failure mechanisms, matrix crack, fiber breakage, and delamination were captured by the prediction. The reported experimental results showed the ability of the peridynamic theory to realistically capture failure initiations and propagation in composites. Karakuzu et al. Analyzed woven glass vinylester composite material plate with two pin-loaded holes. The aim of this study was to investigate the effects of geometrical parameters such as edge distance to hole diameter, plate width to hole diameter, and the distance between two holes to holes diameter ratios on failure loads and failure modes. Problems have been analyzed experimentally and numerically. By increasing all three ratios, the ultimate load capacity is increasing. Then Gezo et al. Analyzed the stress distribution under in-plane tension loading between two open holes that were set parallel and orthogonal respectively with respect to the load direction for different symmetric carbon fiber laminates. They concluded that the stress concentration factor is not affected by the distance between the hole centers for specimens with holes located parallel to the load direction. Moreover, they investigated the minimum distance at which hole interactions begins for specimens with holes located orthogonally to the load direction. The two hole interactions for composite materials were studied by Ozaslan et al. Stress analysis and strength prediction were performed for carbon epoxy laminates with holes in specific orientations. To set a distance between two hole centers, interactions between two holes separated by several distances was examined. Hole center distances were set to 1.5 times the hole diameter. Experimental and numerical methods was used to predict final failure load. Point stress criteria and extended point stress criteria methods was used. Point stress criteria method is a stress-based failure criteria. According to this method, failure occurs when the stress at the characteristic distance away from the hole tip reach unmatched plate strength. The point stress criteria method cannot be performed when the critical region is in the highly nonlinear region. Therefore, this method is extended by using failure strength of specimens. The extended method was verified experimentally. The strength of the specimens was significantly affected by the hole orientations. Three cases are examined. One is with one hole to the free edge, and the other two are interactions between two holes separated by several distances. The material used is carbon epoxy laminates with the orientation given. Stress and displacement calculation have been done with finite element methods in ANSYS. The finite element analysis stress results have been validated with results of Ozaslan et al. The bond-based peridynamic model has been modeled in MATLAB. The displacement has been calculated with bond-based peridynamics and compared with the results of finite element analysis. The model is shown in this figure. As you can see, the coordinate system is in the center of the plate, and the pressure is applied on the short edge in x direction. Three cases have been studied. The path is defined perpendicular to the applied load. First case specimen is OHT1 with centered hole. Its path 1 is from hole edge to plate free edge. Second case specimen is OHT2-1 with two holes at x equals 0. Its path 2 is between two hole edges. The distance between holes in y direction is 3 times the hole diameter. Third case is specimen OHT2-2 with two holes at x equals 0. Its path 3 is between two hole edges. The distance between holes in y direction is 1.5 times the hole diameter. Carbon epoxy laminate is analyzed. The orientation is given. The laminate has 8 plies and is symmetric. In-plane engineering constants is calculated for bond-based peridynamic code and finite element method. In-plane engineering constants is engineering constants due to the global coordinates. The constants are calculated from extensional compliance matrix. Since the laminate is symmetric, the coupling stiffness matrix becomes 0. The extensional compliance matrix is equal to inverse extensional stiffness matrix, and bending compliance matrix is equal to inverse bending stiffness matrix. In the bond-based peridynamic code, the peridynamic mesh is defined by material points and their bonds with other material points inside the horizon. Horizon is determined as 3.015 times the spacing between material points. For the x material points shown in figure, the other materials inside the horizon is x material point family. For making holes with the peridynamic mesh, the material points inside the hole are erased and formation of material bonds is prevented. Peridynamic bond constant. One bond constant for isotropic material is defined. Because an isotropic material is independent of directions, isotropic bond constants depends on elastic modulus, horizon, and thickness. Composite fiber reinforced materials is directional dependent. Therefore, two bond constants are defined. One in fiber direction, the other in arbitrary direction. The bond constant in fiber direction depends on stiffness matrix, which is calculated by orthotropic engineering data, and initial distance. The bond constant in arbitrary direction depends on stiffness matrix, horizon, and thickness. Defining mesh in finite element method, a square with the holes in center, rings around the holes, and lines on the symmetric planes is defined for fine mesh definition. Outside the square, mesh is coarse. The boundary conditions are defined in static structural. The specimen is loaded in tension. Pressure is defined in direction of x-axis on the short faces. For fixing the model, displacement equals 0 is given to nodes at the center of xz symmetry plane in x direction and at the center of yz symmetry plane in y and z direction. Finite element method validation is done with Ozaslan et al. The validation is done separately for the three cases. On the laminate stress in x direction contour and on the laminate stress to x position figure, it's clearly seen that the holes in OHT2-2 specimen do interact. The maximum stress occurs on the hole edge for all cases. Bond-based peridynamic theory results validation is done with finite element analysis. Deformation in y direction due to y coordinates is figured. The finite element analysis contour and bond-based peridynamic contour looks pretty similar. The validation is done with finite element analysis. Deformation in x direction due to x coordinates is figured. Each case are figured separately. Finite element analysis and bond-based peridynamic figure gradients and contours are similar. The results of finite element analysis are compatible with Ozaslan et al. You can see a table which shows laminate stress values for finite element analysis and Ozaslan et al. the error is quite low. Peridynamic deformation in y direction, the maximum deformation occurs in specimen with hole distance 3 times the diameter. The reason is normally maximum y deformation occurs near the free edge under tension, and the holes in this case are near the free edge. Peridynamic deformation in x direction, it was assumed that x deformation for the specimen with two holes would become the same value. The difference is given and is quite small. The reason is the number of material points in solution of OHT2-2 is more than the other specimens. Because the spacing between hole center is small and more material point has to be defined on the path for accurate solution. In the future, the bond-based peridynamic model with two hole interactions with different angle orientations effect and different composite material orientations will be analyzed. The crack propagation will be modeled for each angle and material orientations. As shown in the figure A, angle is added to the model. This work is supported by TÜBİTAK project number 115M585. Thank you for listening. If you have any questions, I will be pleased to answer. You can find my email address on the front page.